This is the sample exam for the final. I have 20 problems here. Let's go through these. The first, find the volume of the solid formed by revolving the region bounded by the graphs of y equal to x squared plus 2, y equal to 2, x equal to 0, and x equal to 3. About the x-axis, and you want to use the disk method. Let's get the graph of this. We have a parabola. I guess I can do better. And we'll just call it y sub 1. We'll call this y sub 2. And of course this parabola does not curve back in, but my crippled left hand gets the best of me sometimes. And then you got x equal to 0 and x equal to 3. It's really just that part there is what you have, this region inside here. That's what we're focusing on. And so this is y sub 1, y sub 2, and this is x equal to 3. And over here at this, this line here that gives us this tip is x equal to 0. And so from this, we want to be able to form the equation. And we're talking about the volume using the disk method. So this is pi times the integral from a to b. We have to use the shell method because notice here that we do have a hole that you want to minus out. And this is the point, y equal to 2. So this would be r of x to be squared minus little r of x squared dx. And so notice here that capital R of x would be y sub 2, and then little r of x is just y sub 1. So this is little r of x, this is just 2, and capital R of x is x squared plus 2. And we know we're dealing in terms of x's because we revolve this about the x-axis, and for the disk method the radius is perpendicular to the axis of revolution. And so this radius has a thickness of delta x. So that's why our functions in terms of x. And so we have to minus out the hole, and the hole is this region in here that we have to get rid of, and that's just the distance of 2. So this volume comes out to be pi times, we're evaluating this from x equals 0 to x equal to 3. Capital R, the big radius, is x squared plus 2, that's all to be squared, minus the little guy, that's 2 to be squared, dx. So we get pi times the integral from 0 to 3. And in here we simplify this out. Before all that, you get x to the 4th plus 4x squared plus 4 minus 4 dx. So we get pi times the integral from 0 to 3 of x to the 4th plus 4x squared dx. Now you integrate, we have pi times 1/5 x to the 5th plus 4/3 times x to the 3rd, evaluated from 0 to 3. We have pi there, and then we have 1/5 times 3 to the 5th plus 4/3 times 3 to the 3rd. And then you simplify all of that on the calculator and you get 4/23 divided by 5 pi. Is that okay? So now let's look at number 2. Number 2, here we want to use the shell method to find the volume generated by revolving the plane region of the two functions about the y-axis. So we have, let's say y sub 1 is x squared and y sub 2 is 4x minus x squared. Well, we have two parabolas, and this is a problem that we've seen in class so many times. So you have the parabola that concaves upward, is the x squared, it's doing that. Then you have the parabola, this guy is y sub 1. Then you have the parabola that concaves downward, y sub 2. You know, it's doing all of that, but you don't need all of that. You just need the region that's bounded. This guy right here is y sub 2. We're going to revolve this about the y-axis, and for the shell method, the radius of the slice that you take, the rectangular slice, is parallel to the axis of revolution. Now, there's a couple of things we need here. We need the distance from the axis of revolution to the center of the rectangular slice. You call that P. And then we need H, so-called height. And so P is, look, this thickness is delta x, and P travels a distance of x. So P is equal to x, and H is equal to y sub 2 minus y sub 1. So this is 4x minus 2x squared. Now I need this point and I need this point. Well, this first point here is the origin, so it's obvious, 0, 0. Got to find this point here. Well, that's where these two so-called functions intersect, and to see where they what points they give you, you set the two functions equal. So x squared is equal to 4x minus x squared, and so now we get 2x squared minus 4x equal to 0. Factor out of 2x, we get x minus 2 equal to 0. So x equal to 0, and then x equal to 2, So we're going to evaluate this integral from x equal to 0 to x equal to 2. So the volume here, using the shell method, has the formula 2 pi times the integral from a to b of p times h. You know, it's p of x, h of x. Let's put that mess in there to make it professional, right? P of x times h of x dx. So the volume is equal to 2 pi times the integral from 0 to 2. P of x is x, and h of x, we found that guy to be this, 4x minus 2x squared dx. Now we integrate. So the volume is 2 pi times the integral. Let's simplify. 4x squared minus 2x to the third dx. So the volume is 2 pi. We integrate now. We have 4 thirds x to the third minus 2 divided by 4, 1/2 x to the fourth. Evaluate it from 0 to 2. And we simplify all of that. This is 2 pi times, let's plug in the 2 for x, so we get 2 to the third, that's 8. We have 4 times 8 divided by 3, minus 2 to the fourth, 16 divided by 2. Keep on simplifying. 2 pi times the 32 over 3 minus 8. So we get 2 pi times 32 minus the 24, so that's 8 thirds, and we get 16 pi over 3. And that's what you want for the volume that we found using the shell method. Number 3, we're going to find the arc length. They give us a function f of x is equal to 2/3 times x minus 8 to the 3/2 power on the interval from 8 to 16. Well, you need the derivative for the arc length, so this is 2/3 times 3/2 times x minus 8 to the 3/2 minus 1. We get the 1/2 power, so we have x minus 8 to the 1/2 power. So the arc length is the integral from 8 to 16 of the square root of 1 plus the derivative squared dx. So that gives us the integral from 8 to 16 of the square root of 1 plus x minus 8 to the 1/2 to be squared, and we just get this. Here, this guy's the 1/2, but that guy's being squared dx. So the arc length is the integral from 8 to 16, just the square root of x minus 7 dx. Integrate that. Let u equal to x minus 7. du is dx. So we get the integral from 8 to 16 of u to the 1/2 du. So now we get u to the 3/2 divided by 3/2. Well, the x is evaluated from 8 to 16. So this is 2/3 times x minus 8 to the 3/2 evaluated from 8 to 16. Took my sins and put them in a bag. So 2/3. Let's plug in the x to be 16. So 16 minus 8 gives us a 9. So we have 9 to the 3/2 minus 2/3. Evaluate x minus 8 to the 3/2 at this is a 7, not an 8. And so 16 minus the 7, now that makes sense, will be this 9. Cuckoo. Okay, now we plug in the 8 minus 7, we get 1 to the 3/2, that's just 1. So we simplify this, we have 2/3, and then this is 9 to the 3/2, that's 3 to the third, so we get 27 minus 1. So we get 26 times 2, that's 52 all over 3. Alright. So nothing strange about that. Number 4. Evaluate this integral. With this guy, you got to complete the square downstairs to see exactly what it is. So we have 6x minus x squared. We go on the side and take care of that. This is minus x squared plus 6x. You factor out a negative, so we have x squared minus 6x. Complete the square on the 6. Take half of 6, we get 3, and then we square that, we get 9, so we say plus 9 minus 9. Take the negative guy out. The negative 9 times this negative 1 would give us a positive 9 on the outside, so we have 9 minus x squared minus 6x plus 9. This is 9 minus x minus 3 to be squared. So we come back up here, we plug that in. We have 3 all over the square root of 9, which is 3 to be squared, minus x minus 3 all to be squared dx. This is a known formula for the sine inverse. So this 3 is on the outside. This is 3 times sine inverse of this term divided by that. X minus 3 all over 3 plus c. Okay, be happy with that. Number 5. Number 5, you want to evaluate this guy using integration by parts. The integral of the natural log of x all over x squared dx. Let's let u equal to the natural log of x, and dv equals the 1 over x squared, or x to the negative 2 dx. So du is 1 over x dx, and v, we integrate dv, we get this guy's integral. So I get v to equal, this is x to the negative 2 plus 1, that's negative 1 all over negative 1, or just negative 1 over x. So using the form for the integration by parts, this becomes u times v. So this is, yes, negative the natural log of x over x minus the integral of v du. Well, v is that negative, so negative times negative is positive. Hello, somebody. 1 over x. This is uv minus the integral of v du. And du has a 1 over x there. And I'm forgetting that. So get out the way, dx. Let's put that guy in there. So this is uv minus the integral of v du. That du, oh succotash, it's right there. That's 1 over x dx. Now we can begin. And so we have negative the natural log of x over x plus the integral of 1 over x squared dx. Well, we just did the integral of 1 over x squared, which was that, and we got negative 1 over x. So instead of doing the same thing over again, we just use what we got. You got to use what you got to get what you, whatever, some old blues song. So this is just the integral of 1 over x squared is negative 1 over x plus a constant. You can factor out negative 1 over x just to make it look pretty. This is 1 over x, and then just going to put this positive 1 first, then plus the natural log of x, and plus c. And you know, of course, I take this or that right there. It's fine. Number 6, got to use some partial fractions on that one. So we have the integral of 4x squared plus 2x minus 1 all over x to the third plus x squared dx. So let's look at the fraction by itself. So this is 4x squared plus 2x minus 1. This is over x squared times x plus 1. Now we do our partial fractions method. This is a over x plus b over x squared. You have a repeating term. This is how we write it. This is how we do it. Okay, plus c over x plus 1. Now you multiply both sides of this equation by the LCD, and that gives us the left side 4x squared plus 2x minus 1 is equal to a times x plus 1 plus b times x plus 1 plus c times x squared. Well, let x equal to 0, and that'll help us get rid of, this guy and that guy. Plug in a 0 here and a 0 there, would cancel out the a and the c. We could solve for b. So if x is 0, put in x equals 0 there, wherever you see x, right? So I get negative 1 on the left side is equal to the b times 0 plus 1, and so b is equal to negative 1. Now let x equal to the negative 1, and that will cancel out the a and the b, and then we can work on solving for c. So let x equal to negative 1. So on the left side, do the same thing. Plug in x equal to negative 1 wherever I have x. So I get 4 minus 2 minus 1 is equal to x being negative 1. I end up with just c, because x equal to negative 1 here makes that a 0, and this guy gives you a 0 as well. So I have c here is equal to 1. Now I have to solve for a. The only trouble about this is that I have nothing else to say let x equal to give me what I want, and so I have to look at corresponding expressions of an equation. The corresponding components are equal. So let's see. I have on the left side 4x squared plus 2x minus 1 is equal to, all I'm solving for is a. Notice that on the right side I get a times x squared plus, just simplifying everything out, ax plus bx plus b plus cx squared. Now look at where I have the a, and you can use the ax squared plus the cx squared, if you will, or you can use these two guys. I'm going to use the ax squared plus cx squared. On this side, this guy would be equivalent to the sum of those two on the right. So I get 4x squared has to be the same thing as ax squared plus cx squared. So here I have 4x squared plus, not plus, equal, is equal to a plus c times x squared. So that gives me 4 is equal to a plus c. Now I have c equal to 1, and so I have 4 is equal to a plus 1. This implies that a is equal to 3. Right. So I come back up here and I can write this now as the integral, looking at a over x. A is 3, so this is 3 over x, plus now b over x squared, but b is negative 1 over x squared, and then plus c, that's plus 1 over x plus 1. That's a plus. Okay. all this stuff is in a bag. Integrate here, and we have, let's put it in red. So this is 3 times the natural log of the absolute value of x. You integrate the 1 over x squared. If you recall, this is negative in front there. Negative 1 over x squared dx. This is negative times the integral of x to the negative 2 dx. So this guy is the negative. Then I have x to the negative 2. X to the negative 2 plus 1 is negative 1 all over negative 1. So I just get 1 over x. So this guy right here is plus 1 over x plus the natural log of the absolute value of x plus 1 plus c. I get the like terms together, and you can use just the rule in algebra with the natural logs, and the addition becomes a product. So this is 1 over x, this term here, plus the natural log of the absolute value of x to the third times x plus 1 plus c. Okay, how you like me now? Right. Let's look at number 7. Use L'Hopital's rule to evaluate these limits. The first is the limit as x goes to infinity of the natural log of x all over x squared. So you plug in x to be infinity, and this gives you infinity over infinity. Well, this is an indeterminate form. And we said that if it's an indeterminate form, you can use L'Hopital's rule. You got 3 choices. You can factor, rationalize, or use L'Hopital's rule. So here, the instructions tell you to use L'Hopital's rule. So you take the derivative of the numerator. So this guy is the limit as x goes to infinity. The derivative of the numerator is 1 over x. And the derivative of our denominator is 2x. This is the limit as x goes to infinity of 1 over 2x squared. And as x goes to infinity, 1 over 2x squared goes to 0. That's our limit. Part B, the limit as x approaches 2 from the right of 1 over x squared minus 4 minus the square root of x minus 1 over x squared minus 4. So we simplify this. This is the limit as x goes to 2 from the right. This is 1 minus the square root of x minus 1 all over x squared minus 4. Now you check. Let's plug in x equal to 2. So we get in the numerator 1 minus the square root of 2 minus 1. That's 1 minus 1. We get 0. And then we plug in x equal to 2 downstairs. That's 2 squared is 4 minus 4. We get 0. Another indeterminate form. So it's safe to use L'Hopital's rule. You have to always check that. If not, then you cannot use L'Hopital's rule. The limit has to be of an indeterminate form nature. So take the derivative of our numerator. So now we have the limit as x goes to 2 from the right. This is just negative 1/2 times x minus 1 to the negative 1/2 divided by 2x. And this is, yes, the limit as x goes to 2 from the right. It's negative up top all over 4x times the square root of x minus 1. Now we plug in x equal to 2. So we have negative 1 all over 4 times 2 times the square root of 2 minus 1. That's just 1. So we get negative 1 over 8. So, you know, the limit of a constant is a constant, and the constant there is negative 1 over 8. Number 8. Determine the convergence or divergence of the sequence. If the sequence converges, find its limit. They give us a sub n is equal to 1 plus k over n to the nth power. You want to find the limit as n goes to infinity of a sub n. This is the same thing as the limit as n goes to infinity of 1 plus k over n to the nth power. Here, let's let y equal to what we're looking for. The limit as n goes to infinity of 1 plus k over n to the nth power. Now, I have this power of an n, which is difficult to deal with, but I do have help from algebra in terms of the natural log. So let's take the natural log of both sides. This is the natural log of y is equal to the natural log of the limit as n goes to infinity of 1 plus k over n to the nth power. This the sequence is continuous on this interval, open interval from 0 to infinity. Open interval from 0 to infinity is not continuous at n equals 0 because I have an n in my denominator, and you don't want your denominator to give you 0. So it's continuous since the sequence is continuous on the open interval from 0 to infinity. This implies that I can interpose these two statements. So this implies that the natural log of y is equal to the limit as n goes to infinity of the natural log of 1 plus k over n to the nth power. Now, when you check this to see if this is an indeterminate form, I have the natural log of 1 as n goes to infinity. I have the natural log of 1, which is 0, raised to the infinite power. So basically here I get 0 raised to the infinite power, which is also an indeterminate form. So it's safe to use L'Hopital's rule, but for L'Hopital's rule you got to have something divided by something else. So we can manipulate this using our algebra. So here I have the natural log of y is equal to the limit as n goes to infinity of the natural log of 1 plus k over n divided by 1 over n. Because that 1 over n downstairs just becomes n in our numerator, and I better not skip the step, right? I have skipped a step. I don't want to throw you off. So this is n times the natural log of 1 plus k over n. So now I can write this as, this is the natural log of y is equal to the limit as n goes to infinity of the natural log of 1 plus k over n divided by 1 over n. That 1 over n downstairs is the same thing as n in our numerator, Hello, somebody. And so this is the natural log of y is equal to the limit. When I get here, let's go back. This is the limit as n goes to infinity. Now you look at what you have, and if I check to see if this guy will be of an indeterminate form, then I have the natural log of 1, which is 0, and then as n goes to infinity, 1 over n goes to 0. So this is still an indeterminate form, and so this gives me the process whereby I can apply L'Hopital's rule. So when we do that, we have here the derivative of our numerator, which is 1 over 1 plus the k over n times the derivative of that denominator, so the derivative of 1 plus k over n is the derivative of 1, that's 0. And just put it here, the derivative of 1 plus, this is k times n to the negative 1. So this is negative k times n to the negative 2. And so this is just negative k over n squared. So that's our derivative. Negative k over n squared. And this is all over. This is divided by the derivative of this guy, the derivative of the 1 over n. Well, the derivative of 1 over n is just negative 1 over n squared. Negative 1 over n squared. We'll look at the things that cancel out. The negative signs will cancel. The n squares will cancel. Close that up. So I have the natural log of y is equal to the limit as n goes to infinity. This is k all over 1 plus k over n. Now take the limit, and so the limit of k over 1 plus k over n, we'll notice that this guy goes to 0 as n goes to infinity. K is a constant. As n goes to infinity, k over n goes to 0. Just that part, not the whole thing. So I have the limit of k over 1, which is just the limit of a constant is a constant. But this implies that I have the natural log of y is equal to k. That is to say, y is equal to, by definition, e to the k. But y is what we had said in this let statement. So we conclude that y is the limit of the sequence, the limit of 1 plus k over n to the n is equal to e to the k. And look, e to the k is finite. So if the limit of a function is finite, then the limit exists. The limit exists, and is equal to e to the k. That's it. Okay. Number 9. Number 9, find the sum of the convergent series. We have the summation as n goes from 1 to infinity of 4 over n times n plus 4. We've got to use partial fractions to break this down. So we have 4 over n plus 4. This is equal to a over n plus b over n plus 4. And so we simplify this, multiply both sides by the LCD. We get 4 is equal to a times n plus 4 plus b times n. Let n equal to 0, and we get 4 is equal to 4 times a. So a is equal to 1. And then let n equal to negative 4. We get 4 is equal to negative 4b. So b is equal to negative 1. So you come up here, based on this is the summation as n goes from 1 to infinity of a over n, looking at this, where the a is the 1 over n, plus b, which is negative 1 over n plus 4. So now we list these summation values out and see where we're going. Recall, anytime we use partial fractions, we use the telescoping method. So this is the summation of 1 over n minus 1 over n plus 4. We start with n equal to 1 because it tells us that. So when n is 1, we get 1 minus 1 over 5, plus n is 2, we get 1/2 minus 1/6, plus when n is 3, 1/3 minus 1 over 7. When n is 4, we get plus 1/4 minus 1 over 8. Let's go a little bit further, plus 1/5 minus 1 over 9, plus 1/6. Minus 1 over 10, plus and so on. Hit the last term, minus 1 over n plus 4, and so on, right? Let's see what cancels out. The 1/5 cancels out. 1/6 cancels out. The 1/7 would cancel out over there. The 1/8 would cancel out over here. The 1/9, and so on. 1/10. Oh, not the 1 over n plus 4. Sorry. That's the last term that we pick up, so we need that guy. So we say that this sequence has the sequence of n terms looks like this. 1, that's right, what we have left, plus 1 over 2, plus 1 over 3, plus 1 over 4, and then minus 1 over n plus 4. The minus 1 over n plus 4 would help us get those last terms way out yonder. So now let's simplify this. This s of n, simplify, adding these terms up. You get 25 over 12 minus 1 over n plus 4. You take the limit of s of n as n goes to infinity, that gives you the sum. Well, let's see. So this is the limit as n goes to infinity of 25 over 12 minus 1 over n plus 4. As n goes to infinity, 1 over n plus 4 goes to 0. I have left with just a constant, 25 over 12. So s, that means the sum, which is also the limit, is equal to 2 1/12. Okay? So let's see, what else do we have? And so you find the sum of the convergent series, and whenever you have to use partial fractions, just always note you've got to use the so-called telescoping method. Number 10. number 10, you want to determine whether or not this series is convergent. So we have the summation as n goes from 1 to infinity of 1 over n times n squared plus 1. And we're going to compare this to a known convergent series compared to the summation as n goes from 1 to infinity of 1 over n cubed. Notice that the problem that we're given looks like that. If you think about it, if I didn't have that plus 1 there, I would have 1 over n cubed. This is a known convergent p-series. My left hand does not want to act right today. Convergent p-series. But notice that n cubed is less than this n cubed plus n, for n that are natural numbers, right? Going from 1 to infinity. So if that's the case, then we also get that 1 over n cubed plus n is less than 1 over n cubed. And so based on the principle there for the limit comparison, or the direct comparison, and this is what we're doing here with the so-called direct comparison. Direct comparison test. If we have this, where I know that this guy's series is convergent, anything before it, any other series before it has to also converge. So by direct comparison, since the summation of 1 over n cubed converges, then the summation of the problem that we're given of 1 over n times n squared plus 1 also converges. Now if we had gotten greater than instead of less than, I can't use this direct comparison test. This test is not applicable. I got to do something else. Wouldn't be able to determine the convergence or divergence of the particular series at hand if this inequality was the other way. Okay. So now number 11. Summation as n goes from 1 to infinity of 3 to the n all over n cubed. I'm going to use here the ratio test. It'll be difficult to use the nth term test. So for the ratio test, we have the limit as n goes to infinity of the absolute value 3 to the n plus 1 over n plus 1 cubed divided by 3 to the n all over n cubed. This is the limit as n goes to infinity of the absolute value. To simplify what we have, this is n cubed, which comes upstairs, times 3 to the n times 3, and this is now all over 3 to the n times n to the 1, n plus 1 to the third power. You can drop the absolute value because everything that we have in there is positive. 3 to the n's cancel out, so I have the limit as n goes to infinity of 3n cubed all over n plus 1 to the third. And just finding the limit using the horizontal isotope rule, if my degree in my numerator is the same as my degree in my denominator, then the limit, or the horizontal isotope, is the ratio of the leading coefficients, which is just 3. 3 divided by 1 is 3. Now for the ratio test, for the series to be convergent, for the ratio test, the limit of the ratio must be less than 1. But this guy is greater than 1, so this implies that the series diverges. Okay. Number 12. Use a fourth Maclaurin polynomial of f of x equal to the natural log of x plus 1 to approximate the natural log of 1.1. So let's start with this. Notice that 1 over 1 plus x, just based on what we talked about for the power series, is the summation as n goes from 0 to infinity of negative 1 to the n times x to the n. You got the natural log of x plus 1, which would be the integral of this. So notice that the integral of 1 over 1 plus x dx is what you want. It's the natural log of absolute value of x plus 1. So then I can, if I take the integral of this side, take the integral of that side. So this is the integral of the summation as n goes from 0 to infinity, negative 1 to the n of x to the n dx. This gives me the summation as n goes from 0 to infinity of negative 1 to the n of x to the n plus 1 divided by n plus 1. So you want to do the fourth Maclaurin polynomial, and that simply means here that we're going to go out actually 5 terms. So we're going to take this summation list these guys out, list 5 of them. Why is it 5? Well, let me show you. When n is equal to 0, here we get, if you look at that, you get x. N is equal to 1, this is negative x to the second all over 2. When n is equal to 0, 1, this is n equal to 0, n equal to 1. And when n is equal to 2, then negative 1 to the second is positive. Get x to the third all over 3. But this is when n is equal to 2. Minus, this is alternate, x to the fourth all over 4. This is n equal to 3. They want you to go out 4 times. Plus x to the fifth all over 5. N is equal to 5. So you get 5 terms there. So when they say x, check this out. Notice that you had the natural log of x plus 1. So I want this to equal the natural log of 1.1. Well, this is the natural log of 1, which is, look, you got this x plus 1. So you think about this guy as being, let me write it the way it's given. So this would be 0.1 plus 1. So this is the 1 here, and then this 0.1 becomes the x, right? So I'm going to replace this x, the these x's there with 0.1. So I get the natural log of 1.1 is equal to 0.1 minus 0.1 to the second all over 2 plus 0.1 to the third all over 3 minus 0.1 to the fourth all over 4 plus 0.1 to the fifth all over 5. And you hit that on your calculator and just punch that in, and you get 0. Calculator. Get 0.09531. Now you check that on the calculator. Just type in the natural log of 1.1 and you get, whoa, hey, we're dead on it. Okay, pretty cool stuff. Number 13. Find a power series for the function g of x equal to 1 over 2x minus 5, centered at c equal to -3, and then determine the interval of convergence. But let's take this function g of x. So this is 1 over -5 plus 2x. This is equal to 1 over -5 plus 2. Look, you got to have x minus c. So x minus c is x minus a -3. So this is x plus 3. So, but I can't harm this problem, so I have to say minus 3 as well. So it's still the original form. Simplify. This is 1 over -5 plus 2 times x plus 3 that you got to have in there. Take out the negative part, that's -6. So I get 1 over -11 plus 2 times x plus 3. And this is 1 over, let's factor out -11 from downstairs. That's 1 plus 2 times x plus 3 all over -11. This is -1 over 11 times what I have left. This is 1 minus 2 times x plus 3 all over 11. And then just by the definition of how we define the power series based on the geometric series, you get the -111 sitting on the outside times the summation as n goes from 0 to infinity of 2 times x plus 3 all over 11 to the n. And you can take this 11 and hook it up there with this guy and have in the bottom 11 to the n plus 1, whatever. That's fine. I mean, you just leave it like that, and I'm happy with that. Now, to determine the interval of convergence, you recall that all you want to do is apply the ratio test. So here we have the limit as n goes to infinity of the absolute value of 2x, simplifying that, plus 6 over 11 to the n plus 1 divided by 2x plus 6 over 11 to the nth power, and we get the limit as n goes to infinity of the absolute value of this 2x plus 6 all over 11. For this guy to be convergent, you want this guy to be less than 1. Notice that the limit of this, there's no n in here, right? This is as n goes to infinity. Well, since there's no n, 2x plus 6 divided by 11 is treated as a constant compared to the limitation. So here, the limit of a constant is a constant, so this guy is equal to the absolute value of 2x plus 6 over 11. And for the ratio test to be convergent, you want this guy to be less than 1. So you simplify all of this, and we have, just by definition, this is -1 less than 2x plus 6 over 11 less than 1. And take it up here. Space ran out. I talked too much. So this is -11 less than 2x plus 6 less than 11. Subtract 6, so this is -17 less than 2x less than 5. Divide everything by 2. -17 over 2 less than x is less than 5 over 2. And so our interval is -17 over 2 all the way to 5 over 2. Okay. Alrighty. Number 14. Use Taylor's definition to find the Taylor series for a cosine function. Here's Maclaurin, C is equal to 0. So we have f of x equal to cosine x. Why am I writing that again? I do not know. F of 0 is equal to cosine of 0, that's 1. F prime of x is equal to negative sine x. F double prime of x is equal to negative cosine x. F triple prime is equal to sine x. The fourth derivative is equal to cosine x. The fifth derivative is equal to negative sine x. Now let's plug in x equal to 0. So f prime of 0 is 0. F double prime of 0 is -1. F triple prime of 0 is 0. The fourth derivative evaluated at 0 is 1. And the fifth derivative evaluated at 0 is 0. So we want to write cosine x using the definition of Taylor's or Maclaurin, since c is equal to 0. This guy is f of 0 plus f prime of c. C is 0. Let me just write this, the formula itself, the generic formula, times x minus c plus f double prime at c times x minus c to the second all over 2 factorial, plus and so on, plus the nth derivative at c times x minus c to the nth all over n factorial, and you keep on traveling with that. So this is f of 0, which is 1, then plus f prime of 0, we got plus 0, then f prime, double prime is -1 times x squared all over 2 factorial, then plus f triple prime at 0 with 0, then the fourth derivative, we got 1 times x to the fourth all over 4 factorial. Seems like the signs are alternating on the even terms. So this looks like plus -1 to the n times x to the 2n all over 2n factorial. The terms are even, so that's why we use 2n. And so you conclude that this is the summation as n goes from 0 to infinity of -1 to the n, and this is of x to the 2n divided by 2n factorial, and that's your cosine function represented by a power series. Number 15, we're almost home. Sketch the curve represented by the parametric equations. Here I have x equal to 4 sine theta, y is equal to 3 cosine theta. Notice that x over 4 is equal to sine theta, and y divided by 3 is equal to cosine theta. And we know that sine squared theta plus cosine squared theta is equal to 1. Well, that implies that x over 4 to be squared plus y over 3 to be squared is equal to 1. This is x squared over 16 plus y squared over 9 is equal to 1. This is an ellipse, as we identify what it is. Centered at the origin, and it moves up and down a distance of 3. 1, 2, 3, 1, 2, 3. The center is the origin, and it moves to the left and to the right 4 units. 1, 2, 3, 4. 1, 2, 3, 4. Taking these numbers there, plus or minus 4, plus or minus 3. And you just draw your football. Woohoo! It's an ellipse, right? Shut up. Well, you know, drawing and writing is just not the best in the world. But we bless the Lord anyhow. Number 16. Convert the rectangular equation that we're given to polar form. This is 2y minus 3x equal to 2. Well, y is equal in polar form as r sine theta minus 3, and x is r cosine theta is equal to 2. Factor out of r, we'll get 2 times sine theta minus 3 times cosine theta equal to 2. So we can say that r is equal to 2 all over 2 times sine theta minus 3 cosine theta. Now I did that so that when you look at number 17, you can see how they wrote it, and they wrote it just like this guy. They have r is equal to 12 all over 2 sine theta minus 3 cosine theta. So you want you to convert this guy, graph it, you know, but put the terms in terms of x and y. So this implies that this is no more than, I'm going to multiply both sides by that denominator, so I get 2r sine theta minus 3r cosine theta is equal to 12. Well, this is 2y minus 3x equal to 12. So let's plot a couple of points. I always try to get the intercepts if I can. Let x equal to 0, so y is equal to 6. Then let y equal to 0 and x is equal to negative 4. So we find x equal to 6. Well, excuse me, x equal to negative 4. 1, 2, 3, 4, 2. And y is equal to 6. 1, 2, 3, 4, 5, 6. My graph is not to scale, and I'm going to work on this before I die. Okay, so x is negative 4, negative 1, negative 2, negative 3, negative 4, and y is 6. 1, 2, 3, 4, 5, 6. And just draw a straight line. Mr. Rodney Alfred showed me how to do all the drawing with integrity. But I tell you all the truth, man, I could not remember all that stuff, you know. Just tell me how to turn it on and how to turn it off, and that's about where I am. So it's just a straight linear, you know, line. Okay, let's move on. Number 18. Man, my butt is hurting sitting in this chair. Golly. Okay. Y is equal to 5i minus 3j plus 2k, and v is equal to negative 3I plus 2j minus k. Find the projection of u onto v, and let's see. So I have the projection. Remember that this is w sub 1. This is the projection of u onto v, which is u dot v divided by the norm of v squared times the vector v. Right? So u dot v, we get 5, negative 3, 2, dot product with negative 3, 2, and negative 1. And that gives us, when you simplify all of that, that's negative 15 minus 6 minus 2. And so we simplify all of that, we get negative 23. Then you find the norm of v. That's the square root of the negative 3 squared is 9, plus the 2 squared is 4, plus the negative 1 squared is 1. So we get the square root of 14. So this guy becomes negative 23 all over the norm of v squared, so that's just 14, times the vector v, negative 3, 2, and negative 1. So this guy gives us some fractions, and I had to use my calculator, you know, to make life easier. 69 over 14, comma, negative 23 over 7, or negative 46 over 14, comma, 23 over 14. Okay. And that was for the first part, part A. Part B, W sub 2, you want to look for the vector component of u orthogonal or perpendicular to v. So this is just u minus W sub 1. And u is given as 5 comma negative 3 comma 2 minus this scary vector 69 14 comma negative 23 over 7, and then 23 over 14. And on your calculator, this gives you 1 over 14 comma 2 over 7 comma 5 over 14. And this is a 7 and not a runaway 1. Now number 19, let u and v be two adjacent vectors. Calculate a vector perpendicular to u and v. That's just the cross product. So part A is just u cross with v, I, j, and k. We get u, that's 3, negative 2, and 4, negative 5, negative 1, and 2. And so we work that out, and that gives you, you can do all the work on that. Well, I work it out. I, j, okay. So this becomes negative 4. It's just the cross product of, the cross multiplication of those guys. Negative 4 plus 4. And then for the jth position, delete its row and column. So it becomes the 3 times the 2, we get 6, minus 4 times the negative 5, that's plus 20. then for the kth position, delete its row and column. So we get -3 minus 10. And this cross product gives us -26J minus 13K. Man, that is a sick looking K. Good. Now part B, if I can squeeze it in here, to find the area, that's just the norm of this cross product. That's the area of the parallelogram. So that's the square root of the -26 to be squared plus -13 to be squared, and that gives you 13 times the square root of 5. Now the last problem, woohoo! And man, I'm in trouble. My wife told me to do something, and I'm going to get it. So if you don't see me no more. Number 20. Find the distance between the point. I'm going to call this point Q. 1, 2, 3. And from the plane that's given by 2x minus y plus 3z is equal to 5. Okay. So what we have theoretically is a point Q there, and then we have a plane, and let me back this back. I think I'll just start by just drawing the plane first. That sounds like Bill Clinton. I'll tell you what. I went to Chelsea's wedding. Okay, anyway, Q. 1, 2, 3, and then the point P. The point P is a point that is derived from just the combination of x, y, and z to give you 5. So we'll call this the point P. So if x is 1, y is 0, and if z is 1, then you can get the combination of 5. So the distance between P and Q, the line segment, but I'm looking for this perpendicular. Right? That's the distance. I shoot up here the normal vector. The normal vector n is 2, -1, and 3. This comes right from the A, B, and C terms from the plane, right? And the formula that we're using is the distance is the absolute value of PQ dot with n. That's the dot product divided by the norm of n. So the distance is the dot product of the absolute value of PQ and n divided by the norm of n. So now we can calculate PQ. PQ is equal to 0, 2, 2. And I can calculate the norm of n. This is the square root of 4 plus 1 plus 9, and that gives us the square root of 14. So now the dot product of PQ and n, PQ is 0, 2, 2, and n is 2, -1, and 3. Man, I'm getting hungry. Somebody bring me a chicken sandwich or something, I'll tell you. Anyway, we take the dot product here, we get -2 plus 6, that gives us 4. So the distance is the absolute value of the 4 divided by the square root of 14. Notice that if the dot product is negative, you make it positive because this is the absolute value. So this guy is 4 all over the square root of 14. That's it, right? 4 divided by the square root of 14 is the distance from the point Q to the plane that's given. Well, do well in the final. I wish all of you the best. God bless you. Thank you.